We will discuss on the sampling of analog signals. In our last part, actually, we told you that this is the block diagram. The sensor output should be sent to the input of sample and hold circuit, and the function of the sample and hold circuit is to sample the analog signal. Then it will be sent to AD converter for converting the analog sample values to digital data format. Okay, so for this sample and hold circuit is very important, and I want to discuss this particular theory, sampling theory for analog signals. Here I am showing one analog signal. Suppose a signal is like this. Horizontal axis is representing time, for example, and vertical axis may be any parameter. It may be a voltage, it may be a current, it may be a phasor signal converted to voltage. Ultimately, what I want to say that this will be electrical signal. Okay, so either voltage or current. If it is a pressure signal, then your pressure can be transformed into electrical signal with the help of your sensor. Okay, so sensor output is nothing but electrical signal. So this analog electrical signal, which is a continuous function of time, that will be converted to sample signal, or sampling is required. Okay, so here you see uh, I can sample a signal. Here the most important thing, if the signal is analog or continuous time signal and the amplitude is also analog, then the problem is this: a signal of finite length in general will contain infinite number of points. For example, here from this 0 to 110, within this range, for this particular signal, you can get infinite number of points between 0 and 110. So if you want to store each and the sample values for each and every time instant, then it is not possible, because infinite number of sample values you will get from this signal. So then what we do generally this, we sample the signal with regular interval. We don't take the signal at every point. Rather, what we will take the sample values at different time instants, and the sample values will be regular sample. Regular sample means like this. Here, this is one sample value you are getting at t is equal to 0. Then at t is equal to somewhere here, for example, 10, you are getting another sample value. Then you are getting, suppose at this point another value, at this point another value, so and so. So what I want to say, that at regular time interval you are taking the sample values. You are not taking the sample values in between these two samples. In between these two samples, no signal value or sample value is taken. But here, the problem is this: if you take these sample values, in the right hand side, you see it is these are the sample values taken from this signal. Okay, so here this is the value, so you are getting this value. Then the next sample value is this value is smaller, so you are getting a smaller value. This is further smaller, you are getting this one. Then this one you are getting here. Then this one you are getting here. Then again you are getting this large one. So these are the sample values taken from this analog signal. Now, uh, the problem is this: if you have these sample values in your hand, and if you want to reconstruct the analog signal from these discrete sample values, then we have to raise a question whether it is possible to reconstruct the original analog signal from which we have taken the samples, whether it is possible or not. Is it possible? Now you see, if you want to reconstruct the analog signal from these sample values, then generally what we do some interpolation technique for getting the uh, uh, analog, means getting any value of the signal at any particular instant. So different types of interpolation techniques we have. For example, nearest neighbor interpolation techniques, then your bilinear, nearest neighbor, then linear interpolation technique, Lagrange interpolation technique, Newton interpolation technique. So different types of interpolation we have by which we can find out the signal at any time instant if we have these sample values. That means it is possible to get the analog approximation of this signal. But the problem here, if the sample values are sufficiently spaced with sufficient time gap, then there will be a problem. For example, if you want to get the original signal by using some interpolation technique, for example, you can use sync interpolation technique, then actually what you are doing, you are taking the envelope of this sample values. Okay, envelope means what you will do, let me show it here. This is not working. What happened? Okay. What you will do, just that means you are taking this kind of envelope. So you see, just you are adding these points like this. So you will get, yes?
So it's just your Windows screen, sir, right now.
What happened? But in my, okay, there is a problem. Oh, let me check it. This is due to, is it coming now?
So,
But if it comes here, then it is not coming. It is not coming in my slate, electronic slate. Just 1 minute. Let me make a correction here. Just 1 minute, please. This 1 minute, please. Where is the display property? This is display. Sometimes it is making a problem. One minute. Where is it? Anyway, I have changing this stream minus setting multiple monitors. Okay, let me check it. But here multiple displays, this is not coming here. Why? Where is the problem? This is multiple display. Connect to wireless display. It is written, but this is wireless display. Multiple display is not working. Graphic setting. No. So multiplex advanced display setting, here also we are not seeing this. Anyway, so this is not working. I have to upgrade the software. So there is, at this moment, it is not possible. So, but just let us try to understand from here that here in this case, just you see, if you had, is it visible now?
So,
If you connect these tip points of these sample values, then you will get one graph like this. Yeah, one reconstruction of the analog signal from these sample values. Okay, but the problem in this case, here you see there is a sudden change of the signal up to this value. But if you connect this tip values smoothly in this way, you are not getting a sudden change at this point because you don't know where the where the sudden change in the signal is present. Generally, what you can do, you can smoothly connect these tip points and you can reconstruct the analog signal in this format, in this form. Okay. So this will be the approximate assumption of the original analog signal from these given sample values. These sample values actually have been obtained from this analog signal, but at the time of reconstruction, you are not getting the same thing. This is because actually the distance between two successive samples is very large. Okay. So since the distance between two successive samples is large, so it is not possible to track if sudden change is there in between two successive sample values. But if you increase the sample density, means if you decrease the distance between two successive samples, then it is possible to get the exact means approximate um, form of the analog signal if you apply the interpolation technique. Okay. For example, in this case, you see the signal is same, on the analog signal is same, but we have reduced the sample, the distance between two successive samples. In between two samples, samples, in this case, we have put another sample here. We have taken another sample. So the distance between two successive samples become half of the previous case. Okay, in this case, you see, we are getting one sample at this point and this point. Therefore, if you take the smooth reconstruction like this using interpolation technique, you are getting the interpretation of sudden change. So that means what I want to say, that the distance between two successive samples is very important thing. Whether it is possible to reconstruct the original signal from the sample values, that is dependent on the distance between two successive. At what rate you have taken the samples, based on that, it will be the shape will be protected. Shape of the analog signal will be protected whenever you will reconstruct the signal. Okay. Now, if you further increase the sample density or reduce the distance between two successive samples, then we are getting a better shape. But up to what level we can reduce, and up to what level we can increase the sampling rate, so that after that, means if the sampling frequency, if the sampling distance between two successive samples is greater than that particular critical value, it is not possible to reconstruct the original signal from the samples. Is it possible to determine that critical value? Yes, it is possible to determine at that critical value of the critical value of two successive sample, means critical value of the distance between two successive samples, what I want to say. Okay, it is possible to determine that by developing a theory that is called Nyquist theory. Okay, Shannon-Nyquist theory. So here you see, I just want to uh, develop this theory systematically. Uh, Let us consider this is signal. First, you try to understand the mathematics behind it. Okay, suppose this is the signal, and this signal is represented by this function xt. It is a function of time. Xt is this signal. This is the continuous time signal. Now, this is a pulse train. This pulse train looks like a comb. That is why this pulse train sometimes is called comb function. So st is this pulse train, and you can write st is equal to comb t, and it is nothing but a series of impulse functions. So it can be written as a summation of shifted impulse function like this. I think you know what is the description, what is the definition of impulse function, because in signals and system, this impulse function is already described. So this is the comb function. If you take a series of impulse function like this, that is called actually comb function. Now, if this comb function or this sampling function st is multiplied with this signal, then you will get the sample, okay, sample signal like this. Now here, before that, what I want to
Yes,
say,
sir.
yes,
Sir, in the formula, sir, after comb t, sir, could you explain the delta t minus kts, sir? I can understand this one.
delta t minus kt, you know what is delta t?
Def-
Delta t is a sample at t is equal to 0. It is a delta function at t is equal to 0, and you know the definition of delta function.
Yes, sir.
Okay. Now, if you put k is equal to 0, then it is a delta function. Means it is a delta function at the origin. If you put k is equal to 1, then it will be delta t minus ts. That means the delta function is shifted at ts. Suppose this is your ts. This second sample, this is ts. Then this second sample value will be represented by delta t minus ts. Then if k is equal to 2, then that sample will be delta t minus 2ts. So that this third sample will be delta t minus 2kts. Okay. So in this way, this is the origin, and in the left hand side also you will get the sample values by, but I have not shown here. Okay. In this way, if you get this successive shifted delta functions, and if you add all these things, then you will get this pulse train. Okay, delta t means one sample value at t is equal to 0. Then delta t minus ts means one sample value at ts time instant. Suppose this is ts. Then delta t minus 2ts means single sample at 2ts. Single sample means actually single delta function. This single delta function. Then if you get all the shifted delta functions starting from minus infinite to plus infinite, then that means you are getting all delta functions like this. And if you add all these things, then you will get this train. Okay. It has been started from minus infinity, but I have shown here from 0 to 100, a segment of that. Okay, but ideally it is from minus infinity to plus infinity. Now, if you multiply this is actually comb t function. This looks like a comb, you know, comb by which you just adorn your hair. Okay, so this is like a comb. Okay, so if you multiply this comb function with this analog function, then actually you will get the sample signal. Okay, so sampling means actually multiplication of the analog signal with this kind of comb function. Okay, this is mathematical interpretation, but for this circuit is there. I will discuss about the circuit in the later part. Okay, so here, if I want to find out the condition, condition means if I want to find out the critical value of the distance between two successive samples. Here, distance between two successive samples, it is called actually TS, sampling period. So this is your TS, sampling period. It is the distance between two successive samples. Okay, so this is TS. the distance between this and this TS, distance between this and this TS. Okay, so this TS is called sampling period, and reciprocal of TS is called FS. FS is the sampling frequency. Sampling frequency is the reciprocal of TS. 1 by TS is equal to FS. So sampling frequency is FS and the sampling period is TS. Okay, now the analog signal, this is the analog signal, so it is possible to find out the Fourier transform of this signal. If you take Fourier transform of this analog signal, then you will get the frequency domain description or bandwidth of the signal. Suppose this signal is band limited. Band limited means the signal frequencies are limited to certain range of frequencies, and beyond these frequencies the value of the signal is 0. So here at the left hand side the time domain signal xt is shown, and at the right hand side I have shown, this is suppose the bandwidth or the frequency domain of the signal xf. Xf is the frequency domain of the signal xt, and this is obtained by taking the Fourier transform of the signal. And taking the Fourier transform of the signal, what we see that this is the origin of the frequency. Horizontal axis is now frequency, and vertical axis represents the amplitude at each and every frequency of the signals. So okay. And we see that up to W the signal value is present, and beyond W the signal value is 0. That means beyond this W frequency, for other frequencies which are for which actually frequency is greater than W, for this case actually xf is 0. Okay, similarly this point is minus W. Therefore the bandwidth of the signal is W. It is not twice W, because negative frequency components are not physically realizable. But in spite of that, for the mathematical clearance, I have shown this negative part also, because if you translate the signal from this position to right hand side in another carrier frequency position, then actually this negative frequency will be positive, and it will be clear that negative part was also there in the original baseband signal. Okay, so that's why I will say the bandwidth of the signal is W. Means bandwidth is from 0 to W. The negative part is the replica of the positive part. Okay, so it is not required to mention. And negative frequency components are not also physically realizable. Therefore, the bandwidth of the signal is W. And this kind of signal is called band limited signal, because its bandwidth is limited up to W. Okay, but when you will sample this signal by using a comb function like this, having a frequency fs, sampling frequency fs, then you will get a signal like this. For example, here in this case, the distance between two successive samples is equal to ts, and it can be obtained by multiplying this comb function comb t or st with the analog signal xt. So after multiplication, you will get this representation of the signal. This is the multiplication of xt with the comb function or the sampling function st. Now, this is the time domain sampled signal. If you want to take Fourier transform of this sampled signal, then what will be the Fourier transform? I will show this in the next slide. If you take Fourier transform of this sampled signal, then you will get this Fourier transform of sampled signal. This is XSF. Okay. Now, in this XSF, what we see that original this triangular shaped thing is there. This one. Along with this, we are getting other subbands also having the same bandwidth at every fs time, fs frequency. Here at fs, you are getting another replica of the same thing. Here at twice fs, you are getting another replica of the same thing. Okay, and why it is coming? This is simply done by mathematics. This XSF can be obtained by taking Fourier transform on both sides. So XSF is equal to XF convolve based, because you know, if two signals are multiplied in time domain, in frequency domain, that after taking the Fourier transform, they will be convolved. So you will get the convolution of XF with SF. After convolving these two functions, it is possible to prove that you will get this Fs into summation n is equal to minus infinite to plus infinite Sf minus Nfs, and Xf minus Nfs summation n is equal to minus infinite to plus infinity. This can be represented by this, and this constant term is also Fs, This is this will give you the amplitude of the frequency components. Okay, the scaling of the frequency bands. So you will get this signal, this frequency domain description of the sample signal. So this is the frequency domain of sample signal. Now you see we have so many bands, but which particular band is representing the original signal? This band, this center band, this one. This one is representing the original analog signal. So if you apply some filtering technique, low pass filtering technique, where the filter, low pass filter has a bandwidth at least W, it may be slightly greater than W, it should not be much greater than W, because if it is much greater than W, then this filter will pass some frequency component of this unwanted band also. This other four side bands are unwanted bands. This is unwanted, this is unwanted, this is unwanted, this is only desired band. So I want to filter only this desired band. Okay, if you can filter this desired band, then at the output of the filter will be this one, and this one is nothing but your XF with some scale factor. Okay, so you have to design some filter so that you can get only this, so only this band. So the filter band will be at least W. If it is much less than, if it is less than W, then some frequency components of the desired band will be lost. Okay, and if it is much greater than W, then also the filter can pass some frequency components of this unwanted band. Therefore, it will get some distortion in the resultant signal, output signal. Okay, therefore, the design of filter will be very important thing. What should be the bandwidth of the filter, that will be determined by you by observing the bandwidth of the signal, original analog signal. Based on that, you can design it. Okay. Yes.
Sir, is this the frequency spectrum, sir? The diagram that you showing?
Yes, this is frequency spectrum, because this is XSF and this is F, so it is frequency spectrum, and frequency spectrum is obtained by taking Fourier transform of the time domain signal. Because in signal and system theory, I think you have got this idea. So yes, if you take Fourier transform of a time domain signal, the signal will be translated into frequency domain, and then you will get the description of the frequency, and that is actually frequency spectrum. Okay, so this is the frequency spectrum, and frequency spectrum will tell you how many frequency components are there in the signal, and which are the significant frequency components, which are the frequency component of importance, and which are the negligible, which frequency components can be neglected. Okay, so this is the frequency spectrum of the sample signal, and in this sample signal, frequency spectrum of the sample signal, we see that this is the desired band, and other bands are the shifted bands and undesired. So if you can filter only this much frequency component, then you are getting this, and it is if you get this one, then that means you are getting the signal XT, because this is XF with some constant term will be there. So constant term I am ignoring. Okay, it will be scaled up or scaled down. However, I am setting the constant term as scaling term as 1, then it will be XF. Okay, it looks like this. It looks like this. This is nothing. What is this? This is the Fourier transform of this time domain signal. If you get this one, that means you have got this signal, this analog signal. So here, after filtering, we are getting this one, means we have got the analog signal. So by using a simple low pass filter with proper bandwidth, you can reconstruct the analog signal from the discrete counterpart, discrete or sample signal. So you have in your hand, you have sample signal, and you just send the sample signal through a proper filter, properly designed filter, low pass filter, and at the output of the low pass filter, you will get the analog signal. Analog signal means the analog signal from which you have got the samples. Okay, that means actually signal, the actual signal has been reconstructed at the output of the low pass filter. Yes.
Is there passing the sample signal into the low pass filter, so you have to first Fourier transform it, right? Or will the low pass filter do the Fourier transform also?
Yes, low pass filter characteristics is this one. the low pass filter will pass all the frequency components of the desired band, and it will reject the frequency components of the unwanted bands. That means the low pass filter will reject these four bands, and it will pass at the output only these frequency components. When this frequency component will be passed at the output of the low pass filter, then at the low pass filter output you will get this lower one. This is the low pass filter output. It will reject the other frequency bands. These other frequency band, four other frequency bands, with the side bands, and only the central band will be sent. And this central band is sent at the output, means you are getting at the output of the filter is this. And if this is the frequency band at the low pass output, at the low pass filter output, that means actually you have got this frequency band here, this frequency band. And what is this? This is nothing but this analog signal, because I told you that this analog signal has a bandwidth like this. So you are getting this frequency domain, means in time domain it will be the original signal, original continuous time signal. So in this way, by sending the sample values through the low pass filter, you can reconstruct the analog signal. Okay, but there should be some condition. Obviously, the first condition is the low pass filter bandwidth should be at least equal to the bandwidth of the signal, original signal. Original signal means original continuous time signal. If the bandwidth of the original continuous time signal is W, then the bandwidth of the low pass filter should be at least W. Low pass filter means it is a frequency selective filter. It has a proper characteristics. I am taking this kind of characteristics, this kind of squares, gate shape characteristics. Gate shape characteristics means it will pass this band only at the output of the filter by rejecting this other. So this is the gate, and this gate will pass this band only, and it will reject other four bands. That means at the output of the low pass filter you will get this, which is nothing but the frequency domain of the original and continuous time analog signal. That means you are getting original continuous time analog signal at the output from the sample values. That means the thing is this: it is possible to reconstruct the analog signal from the discrete sample values by using a properly designed low pass filter. Okay, this is the ultimate conclusion from this theory. Clear? Now, next I want to discuss then what conditions should be maintained so that it is possible to reconstruct this signal. Just I will show three band widths, three band structures. Suppose if your sampling frequency 1 by Ts is greater than W. 1 by Ts is greater than W means Ts is less than 1 by 2W. Greater than 2W, sorry. Fs means 1 by Ts is greater than twice W. Means actually Ts is less than 1 by twice W. Ts is less than 1 by twice W. Okay. But let us try to consider this Fs. Then it will be easier for you. If Fs is greater than twice W, then you see between two successive bands, you will get some gap here. You will get some gap between two bands. This is one green band. This is another green band, successive band. Between these two successive bands, you are getting a gap here. This is called guard band. Okay. And why in this case actually you see from here to here W and from this point to this point W. So Fs is greater than twice W. So this is W plus this guard band is equal to Fs. That means Fs is greater than W. Yeah, greater than twice W. Fs is greater than twice W. So when Fs is greater than twice W, then you are getting some guard band between two successive bands. Then it is possible to design some filter which will cover all the frequency components of the desired signal and reject all the frequency components other frequency components, sideband frequency components which are unwanted. So you can design a filter easily. But here in the second case, Fs is equal to twice W. If Fs is equal to twice W, you see this is W and this is also W, and this point is Fs. That means W plus W is equal to Fs. Fs is equal to twice W. So in this case, this boundary, this lowest frequency component of the next band is means just touch the highest frequency component of the first band. This band. Okay, it touches. It touches like this. Here also it touches. Here also it is. Then also it is possible to design. Then also it is possible to design critically a filter like this. So which will only select this band by rejecting the other one. But there is a chance if somehow some error is there. Suppose, for example, your bandwidth of the filter is slightly greater than means just a very small amount of increment is there with respect to W in the bandwidth of your low pass filter, then some frequency component of the next unwanted band will appear in the appear in the filter output. So that will create some unwanted effect that is called aliasing effect. But if you can critically design this filter, then okay. Otherwise, again, if it is slightly less than, then there will be problem. Some frequency components of the desired band will be cut down. You will lose some frequency component. If it is slightly set, if the bandwidth of the filter, low pass filter, is slightly less than W, then some frequency components of the wanted band will be lost. So that will be problem. However, this is the critical point. Okay, but if it is less than, if is less than twice W, so then in that case you see there is overlap between these two bands like this. Now, if you want to get this whole band, this whole unwanted band, obviously some frequency components of the next band which are overlapping with this band, they will appear at the output of the frequency, output of the low pass filter, and it is not possible to avoid this. Okay, so in that case, okay, at the filter output you will get some unwanted frequency components, and the shape of the original signal, shape of the reconstructed signal will be distorted. It will not be equivalent to the original signal. That is called aliasing effect. Aliasing effect. Now, so aliasing effect occurs when Fs means sampling frequency is less than twice W, means twice of the bandwidth of the original continuous time analog signal. Okay, so then what conditions should be maintained for proper reconstruction of the analog signal from the discrete samples? It should be like this. Fs should be at least greater than or equal to twice W. This Fs equal to twice W is the critical point. This is called Nyquist rate. Nyquist rate. And Fs greater than or equal to twice W, it is called actually the condition, Nyquist condition or Nyquist criteria for reconstructing. Yes.
So
Fs.
Sir, could you repeat the criteria, sir?
Nyquist criteria, Nyquist. Nyquist is one scientist. Okay. So Nyquist, Nyquist, Nyquist criteria. Nyquist criteria is this. Here it is written. Okay, Nyquist criteria. Okay. Nyquist criteria means actually Fs greater than or equal to twice W. Under this condition, actually, it is possible to reconstruct the signal without any aliasing effect. So faithful reconstruction is possible in that case. Therefore, Fs greater than or equal to twice W, this is called Nyquist criterion. And Fs is equal to twice W, this is called Nyquist rate of frequency, sampling frequency. At least you have to maintain Fs equal to twice W. If it is below this, if the sampling frequency is below than this twice W, then it is not possible to reconstruct the signal without any aliasing effect. So That is the case. So if is greater than or equal to twice W, that should be maintained at the time of sampling. So whenever you will choose the sampling time period or sampling time, sampling frequency, then sampling frequency should be greater than or equal to twice W, or TS should be less than or equal to 1 by twice W. Where W is known to you, because W is the bandwidth of the analog signal. You can measure the bandwidth of the analog signal, and after that you have to choose the sampling time interval, sampling time interval TS, which should be less than or equal to 1 by twice W. Okay, so then you can apply this you can design some low pass filter by which you can reconstruct the analog signal from the discrete counterparts. Okay, so if fs is less than twice WC, if you filter this, then some frequency component from the next band is coming. But if it is like this, then it is that there is no overlapping. So this is faithful reconstruction, and in this case, the aliasing efforts. Okay. Is this point clear to you?
Yes, sir.
Okay. If you have any problem, you please ask me. All these things are written here, whatever I've just said. Now, in time domain, if I want to say what is the effect of aliasing effect, just I want to see that. Show that here. Suppose this green, this green, it is blue. So suppose this blue is the original signal. This blue, it is high frequency signal. You see, higher frequency signal. This blue is the original signal. Now, suppose this signal is sampled at these points. Okay, so you are getting the sample values at these points. Now, if you get the sample values at these points, then you can predict another signal by satisfying all these points. This is red one. If you reconstruct, suppose these sample values are given in your hand. You have got these sample values. You have to reconstruct the signal by satisfying all these sample values. Now you see this sample values is satisfying this blue signal, because this blue signal is passing through all the sample values, sample points, and at the same time red signal is also satisfying this. Then if I give you these sample values only, then someone may tell that original signal was blue, and someone may tell that no, original signal was red one. Which one was original signal? Blue one. But if someone tells that okay, I am also satisfying this sampling points, sampling values with the help of this red signal, then what is the problem? No. That is the problem actually. This is aliasing effect. So I am giving you some sample values, and when you are reconstructing different signal from those sample values. But if the sampling interval is very, very small, for example, one sample value is there, another 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 sample value is there, then it will be difficult to reconstruct another signal. Then you can get just if you connect those points, you will get unique signal. So that's why I want to say the distance between two successive samples should not be higher than twice W, 1 by twice W. Okay, so TS should not be should not be higher. Yes, TS should be less than equal to 1 by twice W. That means TS should not be higher than 1 by twice W if you want to reconstruct the original signal uniquely. Okay, so otherwise you will get two different interpretations, two different signals from the same sample values. Okay, so this will be the aliasing effect, and this is the representation of aliasing effect in time domain. So if the samples are the distance between two successive samples is very, very large, then you can predict two different signals, more than two different signals you can predict also. No. Okay. So unique reconstruction of unique signal, it will not be possible. So for that reason, this Nyquist criteria should be maintained. Clear? So this is our sampling theory. So today up to this much. Next day I will try to understand how it is possible to sample a signal by using a circuit, by using electronic components. That is sample and hold circuit. Okay. Thank you very much. Is there any question? If you have any question, then please you ask me. Okay. So there is no question. I can leave now. Thank you.
Thank you, sir.
Thank you, sir.